What specific problem does the new method proposed in this paper aim to solve, particularly in the context of artificial neural networks and innate instincts?
The new method proposed in this paper aims to solve the ungrounded alignment problem, which focuses on how to build specific desired concepts into artificial neural networks without explicit grounding or labels during training. This problem is particularly relevant in the context of artificial neural networks as it seeks to replicate innate instincts observed in biological systems, such as a beaver's instinct to build a dam. The paper formalizes this problem through the specific instance of FNORD detection, where the model learns to identify a sequence of images representing characters without any prior knowledge of the characters or their representations. The proposed solution utilizes a bigram alignment loss function to leverage innate knowledge of character relationships, allowing the model to detect high-level concepts from uninterpreted sensory inputs. Ultimately, the goal is to enable artificial systems to exhibit innate drives, akin to biological instincts, in their operational environments.
How does the proposed method for FNORD detection work? Illustrate the approach step by step, detailing the algorithmic components involved in training and testing.
The proposed method for FNORD detection involves several key algorithmic components and steps during both training and testing phases. First, an unsupervised character encoder is trained to map images of letters to class probabilities without any labels, using a batch contrastive loss function that aligns the encoder's predictions with a hard-coded bigram distribution of character sequences derived from English text. During training, the model processes a stream of high-dimensional observations, images of letters, and learns to predict the next character based on the current character's probabilities, leveraging the innate knowledge of bigram relationships among characters. In the testing phase, the model is tasked with detecting a specific trigger word, FNORD, by evaluating sequences of letter images. The FNORD detector sums the log probabilities of the predicted classes for each character in the trigger sequence and compares this sum against a predefined threshold, which is set based on the expected frequency of the trigger in the test set. If the summed probability exceeds the threshold, the detector emits a true response, indicating the presence of the trigger word. This approach allows the model to effectively identify the trigger sequence without relying on explicit labels or feedback during training, demonstrating its capability to generalize across different modalities and representations.
Can you provide a simple yet illustrative example to demonstrate the inner workings of the proposed FNORD detection algorithm, explaining how the algorithm identifies sequences without prior labels?
The FNORD detection algorithm operates by leveraging a bigram distribution of character sequences to identify the target sequence FNORD without any prior labels. For instance, during training, the model receives a stream of images representing letters, such as those from the EMNIST dataset, but it does not know which images correspond to which letters. The algorithm uses a simple two-layer feed-forward network to encode these images into class probabilities. It then employs a batch contrastive loss function that aligns the predicted probabilities from the encoder with the probabilities derived from the bigram distribution, which indicates the likelihood of one character following another, e.g., the probability of n following f. By maximizing the agreement between these two distributions, the model learns to detect the specific sequence FNORD in a new stream of test inputs, achieving over 99% accuracy on the task, despite the absence of explicit labels during training.
What are the theoretical and practical advantages of using your proposed alignment loss function over traditional unsupervised methods such as unigram approaches?
The proposed alignment loss function offers significant theoretical and practical advantages over traditional unsupervised methods, particularly unigram approaches. Theoretically, the alignment loss leverages the innate knowledge of bigram distributions, which captures the relationships between sequential characters, allowing the model to disambiguate characters that may have similar frequencies but different contextual usages. In contrast, unigram models fail to account for these relationships, often leading to poor performance due to their inability to distinguish between characters with similar prior probabilities. Practically, our model achieved over 99% accuracy on the FNORD detection task, demonstrating its effectiveness in detecting high-level concepts without explicit labels, while unigram models struggled to provide meaningful classifications, often resulting in random accuracy. Additionally, the alignment loss function allows for a more robust learning process by maximizing the information shared between the predicted distributions, which is crucial for achieving high accuracy in unsupervised settings. Overall, the alignment loss function not only enhances the model's performance, but also addresses the limitations inherent in traditional unsupervised methods.
How is the effectiveness of the proposed method validated? Please describe the experimental design, including datasets, metrics, and results that showcase the performance of your algorithm.
The effectiveness of the proposed method is validated through a series of experiments using two datasets, permuted EMNIST and permuted CIFAR 100. The model is tasked with detecting the trigger word FNORD in a stream of images representing letters, with no labels provided during training. The primary metric for evaluation is classification accuracy, where the model achieved over 99% accuracy on the EMNIST dataset and 85% on CIFAR 100, significantly outperforming random accuracy of 50%. Additionally, the model's performance was tested on various trigger words of different lengths, demonstrating robustness across different sequences. The encoder also achieved 82% accuracy on single character classification for permuted EMNIST and 23% for a subset of permuted CIFAR 100, further showcasing its capability to learn representations without explicit labels.
What are the limitations of the method presented in your paper, and what future work do you envision to address these limitations or to extend the proposed approach?
The method presented in the paper has several limitations, primarily related to its reliance on a fixed bigram distribution derived from English Wikipedia, which may not generalize well to other datasets or languages. Additionally, the model's performance is constrained by the local optima encountered during optimization, leading to inefficiencies in training, as evidenced by the significant computational resources required. Future work could address these limitations by testing the robustness of the approach across broader modalities, such as different fonts or phoneme-based representations, and exploring how the bigram model could be adapted for larger domains, potentially using predictive models like pre-trained language models. Furthermore, enhancing the optimization process to avoid local optima and developing a curriculum learning approach could improve the model's performance. Lastly, extending the framework to include control systems with innate drives, such as a robot designed to pick up trash, would provide a practical application of the concepts discussed.